the corner store, so I figured let's do some quantum mechanics. So going to be going on with problem 1.9. This is a fun one. And I'm trying this out going into landscape mode. You won't be able to see the whole page at a time, but I hope it's going to be a little bit more zoomed in so it's easier to see. So our first part here is we're going to be finding the probability of finding a particle in this range at time t. So now we're looking for something that the wave function is progressing or changing as a function of time. And we're looking at this idea of, finding that the probability, we want to show that the time derivative of the probability, or of the probability density function integrated from a to b, the time derivative of that, so d dt of the probability density function integrated, well, we have specific limits from a to b, dx psi squared is equal to this j, some function j, evaluated at x equals to a, t minus j evaluated at x equals to b t, where j is a function of x and t, and it is defined as IH bar over 2m psi d complex conjugate of psi dx minus psi complex conjugate d psi dt. So this might look familiar already to you. And the first thing it says to do is to show that this is true. Then it asks what are the units of that. Well, this is where we're going to start, because this should always be your first question. What are the units of this function? So it's called the probability current, because current is going to define something that is per time. Like electrical current is coulombs per time. Water current is volume of water or density of water per time. So it's going to be something per time. Now we have an x, we have a t, so that means that we are going to have units in there of meters for distance and seconds for time. And let's just look at this quickly. So our constants, we have an h bar and 2m. So that's units of joules seconds over kilograms. A joule, the unit of energy, that is a Newton times a meter is a joule. Mass times acceleration times distance is a joule. Seconds, those are just the units of h bar over kilograms. And what we have is area, meters squared, over seconds. So our units are probability current, whereas before our probability curve, if we had some function x, and we take the area under that curve, now we're taking the area under the curve per second. So that should always be our first step when looking at something physical, is at the very least, what units do I have? Okay, now this other part, we want to show that d dt, the full derivative of the probability, is going to equal this guy, and we have this condition. This is I h bar over 2m psi complex conjugate and complex conjugate times the partial derivative of psi with respect to x. I said this might look familiar. Maybe it isn't necessarily that it should be familiar, but it might look familiar to you. I'm going to go ahead and pull up my Griffiths textbook here so I can look at these side by side now, because what I have in my textbook is something that looks a lot like this guy. I have this guy right here, which is looking pretty familiar, right? So I'm basically, what I'm doing to prove that this is true is we're just going to be following the exact steps that we followed to show that the wave function itself, the probability density of the wave function, if we integrate the probability density function with respect to x, that it does not depend at which time we do that normalization, is the reason that we were doing it before. So we just go through the exact same steps here that they have there. So our probability density is just going to be d dt integral a to b dx of psi squared. As we can see here, we could put that inside the integral, and we can rewrite it in this format, which is exactly what our j equals. So this guy is going to equal from a to b dx partial derivative with respect to t of this wave function squared. So that's going to be psi complex conjugate. We work that out using the product rule, so we know that that's going to be, we can write it the same way they did here, or we could write it the other way. We can go ahead and, just to keep this clean, we'll write it this way. Actually, I changed my mind. I'm going to make it the same way as the book did right here. Psi star d psi dt. We could switch up the order. But just for consistency's sake, let's keep it the same. Okay. So now if we plug in our Schrodinger equation, which I did in the video about normalization, we will see that this guy here right here, if we evaluate that out, so if we take the complex conjugate of psi and then multiply it by the time derivative of psi, so if we just plug in this for these terms. Then we can get that simplification. So what I can get here is I get from a to b dx, and now I just have that j function that we had before. So I get this guy right here, and that's what the problem defined as being j. So I know that my time derivative of the probability equals the integral from a to b dx jxt. Oh, and then that's going to be, I left out a dx. So I can pull out an extra, oh, whoops, sorry, those should be x's, not t's. There we go. Those are our second derivatives. And then I can pull out a first derivative from that. So we can go do that step. So that's going to be del x, and then this whole guy. So I can pull out the first single derivative of that, just like we did in our normalization video. And this time I only need the first derivative. Okay, I'll try to write that a little bit more cleanly now. So what I have here is that just following my normalization steps, the time derivative of my probability is going to be the integral from a to b. The integral of the first derivative of I h bar to m psi complex conjugate d psi dx plus d psi complex conjugate dx psi. And I know that because this guy right here is just this guy from our chain rule. Well, we did our chain rule and then we plugged in the Schrodinger equation, which I did not do in this video. That is only in the normalization video that I do all the steps to that. Now we know from our problem statement that this part right here is j of x and t. So my time derivative of my probability from a to b is the integral from a to b dx del x of that current or probability density current. So I take the integral of j of x and t, or I take the derivative and then I take the integral. And integral is just an antiderivative. one outdoes the other one. It's like if you want to undo adding, you do subtracting. If you want to undo subtracting, you do adding. That's how derivatives and integrals work. So that means that this guy is just that integral with those limits from a to b. So my probability is just going to be that evaluated at a and j evaluated at b, which is a pretty nice little result. I did skip most of the steps in that because most of them I did in the video about normalization. So all the steps that you need are all in section 1.4 about how to normalize the wave function. Now this problem does have a second part. I don't remember what it is off the top of my head. So let's go ahead and take a closer look at this. So find the probability of for the wave function in the previous problem. Okay, so that's just find the probability current for the wave function in the previous problem. So that was problem 1.8, whoops, and this was our wave function, and we normalized that so that a was the square root of lambda. So we had our wave function was a is the square root of lambda, e to the negative lambda absolute value of x, and then e to the I omega t. Now we're going to use this definition here. So we have I h bar, and as he says himself, this is not a particularly pithy example. So we get psi del complex conjugate of psi. Oh. And then complex conjugate. I wrote it. Keep writing t's instead of x's. It's not a particularly good habit to have. There we go. And then del x. There we are. Yeah, making sure it was a minus, not a plus. Okay, so then we just plug that in. First thing we probably want to do is just go ahead and take this derivative with respect to x of psi. So that's del x. And then we have e to the negative lambda x, e to the I omega t. That's just going to be square root of lambda e to the I omega t, and our derivative of the inside is negative lambda, derivative of the outside is just the same. So my j of x and t equals, we're going to have I h bar over 2m. I'm going to attempt to pull out all these constants, but it's probably going to be a bad idea because I'm sure I'm going to mess up at some point. So psi and complex conjugate of psi, those both have square root of lambda, and they both have e to the negative lambda square, absolute value of x. I'm going to leave the derivatives alone because I'm not going to try to do too much in one step. Okay, so then we're left with our psi, just has this guy, and then that's going to be multiplied by our x derivative. So that's square root of lambda. We get another one of these guys. Oh, except this one's negative because that's the complex conjugate. Then we have a lambda. Then we have this guy. And then that's going to be minus. Now it's the complex conjugate. And then that whole thing times square root of lambda. And now it's going to be e to the positive I omega t, because that's the x derivative of the regular psi function. And then we have that e to the negative lambda absolute value x. Okay, let's pull out more constants. We have square root of lambda, so now we have a full-on lambda out there. And then we have another negative lambda pull out there, so that's going to be negative. That's going to be a lambda squared. Then what do we have next? We have another e to the negative lambda x. So we got two of those guys. And now we have our e to the i's omega and our e to the I omegas. So we have our complex conjugate and our, so we get this guy, e to the negative I omega t, and then we get e to the negative I omega t, and then we get e to the I omega t. So this is just 1 and 1. And as he said, not a very pithy example. So we don't have a time dependence of that guy. As we can see, our probability density current is constant. So just like velocity is the derivative of the position, we could say like electrical current is the derivative of a charge, time derivative of charge, and our probability density current is our time derivative of the probability. In the previous example, in problem 1.8, we established that our wave function, the probability of finding the particle, was the same for any t. So it did not depend on time. But it was still a pretty fun, it's a pretty fun problem to do. And that's it for problem 1.9. Not much to it.